Welcome to AI Paper Podcasts. We are looking at VGGT Ω today, and honestly, this paper completely rewrites the rules of 3D vision. We are just going straight in. Give me the rapid-fire 50-second summary of what this model actually does.
Okay, so the core breakthrough of VGGT Ω is proving that feed-forward 3D reconstruction models scale predictably. They scale with model capacity and data size in the exact same way large language models do.
Right, which is something the field has been chasing for a while.
Exactly. But to pull this off, the researchers had to solve a massive memory crisis first. So they introduced this thing called register attention, and they just completely streamlined the dense prediction heads.
Okay, and what did that actually do to the performance?
That specific move training GPU memory by 70%.
Right.
And because they freed up all that memory, they were finally able to scale the model up to 10 billion parameters.
Wow, 10 billion.
Yeah, 10 billion. They trained it on 4 million supervised sequences, which is, it's 15 times more data than prior work. Plus, they threw in 18 million unlabeled videos, too.
So what are the actual results? Does it crush the benchmarks?
Completely crushes them. On the Scintille dataset, it improves camera estimation by 77% over the previous state-of-the-art. It runs 50 times faster than optimization methods like MegaSAM, and incredibly, it spontaneously learns to isolate moving objects and align with human language, all without any explicit supervision.
Okay, that is wild. So you've shrunk the memory footprint by 70%. Let's spend some time unpacking the mechanics of how they actually did that. Because if you're listening to this, you know that GPU memory limits are the bottleneck holding the entire 3D vision field back right now.
Oh, absolutely. It's the hard limit on scaling perception models. The issue comes down to mathematical complexity. Standard global attention scales quadratically.
Right, because in standard transformer architectures, you have global attention. Which, for anyone working with high-resolution video, you know that global attention is just an out-of-memory or OER error waiting to happen. If you have ever tried to organize a massive networking event, you understand the absolute chaos of this. Imagine having a room where every single guest is mathematically forced to have a simultaneous individual conversation with every other guest in the room.
Right, it's totally unmanageable.
Yeah, you get 50 people in a room, it's loud. You get 1,000 people. The room just metaphorically catches on fire. Or in our case, your GPU throws an OM error and your entire training run crashes.
That's a perfect analogy. So what the researchers did was they looked at the global attention matrices in the original VGGT model, and they noticed something really interesting. They were incredibly sparse.
Meaning most of the connections were essentially empty.
Right. Most image patches don't actually need to exchange information with patches in other frames. Like if you have a video of a car driving down a street, the pixels representing the sky in frame 1, they don't really need to talk to the pixels of a mailbox in frame 10.
Makes sense. It's just wasted compute.
Exactly. Forcing full global attention everywhere is computationally wasteful. So their solution is this new mechanism called register attention.
Which acts like a system of delegates for that chaotic networking party we were just talking about.
Precisely. So for each input frame, they append 16 learnable scene tokens, which they call registers.
Okay, just 16 tokens per frame.
Right. Then they took the architecture and replaced 25% of the standard global attention layers with this register attention. And in these specific layers, interframe information exchange is strictly restricted.
So the regular image tokens are totally isolated.
Yeah, they don't talk to each other globally across frames anymore. They only talk to their own frame's 16 delegates. And those delegates, the registers, are the only ones allowed to talk to the delegates from the other frames.
Hold on. So they actively broke the architecture. They removed the standard attention mechanisms, restricted the entire multi-frame information flow to just 16 tokens per frame, and the performance didn't drop at all.
Not at all.
How is that mathematically possible?
Well, it works because they created a deliberate functional bottleneck. By forcing all that multi-frame information to squeeze through just those 16 tokens, the network is literally forced to use them to encode highly efficient, high-level global scene summaries.
So it acts like a filter.
Exactly. It strips out all the noise, and just this one architectural change saves about 23% in computational FLOPs and 16% of the memory in the backbone during training.
That's huge. But I want to look at the second major tweak they made to get to that 70% total memory reduction, because register attention was only part of it, right?
Right. The next thing they did was completely gut the dense prediction heads.
Yeah, the original VGGT supervised depth maps, point maps, and tracking features directly through separate physical architectural branches. But VGGT Ω just strips that down to one single dense head for depth and one sparse head for cameras.
Yep, they threw out the rest of the hardware branches.
But, and I think this is the crucial part for the listeners, they kept the multitask loss functions during training.
Yes, and this is a really elegant realization about how neural networks actually learn. They realize the network doesn't need separate physical hardware pathways to learn multitask features.
Interesting. So the loss functions do all the heavy lifting.
Right. The loss gradients alone, like the mathematical penalties applied when the model guesses wrong during training, those are entirely sufficient to shape the latent representations inside the network.
Wow. Okay, let's talk about the convolutions too, because this is where the VRAM savings really compound. High-resolution convolutional layers are absolute memory vampires.
Oh yeah, they eat VRAM for breakfast.
But I think it is important to explain why they eat so much memory. Because it's not about the parameters themselves, right? It's about the activation memory during backpropagation.
Exactly. So when a neural network trains, it does a forward pass to make a prediction and then a backward pass to correct its errors.
Yeah.
During that forward pass through a convolutional layer, the GPU has to save massive high-resolution activation maps. It's essentially scratch paper, so it can calculate the gradients later during the backward pass.
Which is like a filing cabinet that just rapidly overflows the moment you increase the resolution.
Exactly, and you can't even fix it easily with standard techniques like gradient checkpointing. It's just too much data.
So the researchers just ripped them out. They replaced those memory-heavy convolutions with a simple multi-layer perceptron, an MLP, followed by a pixel shuffle operator to upsample the resolution.
Yeah, a much cleaner approach.
And for anyone who hasn't used a pixel shuffle layer before, instead of doing heavy convolutional math to generate new pixels, it just takes a really deep, narrow block of data channels and essentially unstacks them, like laying them out flat into a wider spatial grid.
Which gives you the high resolution you need, but without the massive memory overhead.
Right. So when you combine those three mechanisms, the register attention, the single dense heads driven by multitask loss, and that MLP pixel shuffle, you reduce the training memory footprint to roughly 30% of the original model.
Which is an insane optimization.
It really is. Okay, so you've shrunk the engine down by 70%. But I mean, a smaller, more efficient engine doesn't mean much if you don't have fuel to run it.
No, it doesn't.
If the whole point of this was to scale up to large language model proportions, where do you even find enough clean 3D data on the internet to actually train a 10 billion parameter geometry model?
That was definitely the next massive hurdle. Because in the past, 3D reconstruction models were mostly trained on static scenes. You know, the standard way to get 3D data from 2D images is using structure from motion tools.
Like Colmap.
Right, like Colmap. And Colmap works by looking at fixed static points from different camera angles and triangulating their position in space.
But if you feed Colmap a video of a busy city street, with walking pedestrians and moving cars, it completely breaks down, doesn't it?
Totally breaks down. The algorithm fundamentally assumes the world is completely rigid. So any moving objects just corrupt the geometry calculations entirely.
Which means to unlock internet-scale video, they had to build a massive multi-stage filtration system to actually isolate usable data.
Exactly. They started with 40 million raw internal internet-style videos.
40 million.
Yeah. And first, they used vision language models to pre-filter the data. They intelligently stripped out videos with sudden shot transitions, heavy blur, or just unusable content.
Smart.
Then they ran traditional Colmap, but alongside modern mashing models and the original VGGT model, just to reconstruct the scenes robustly.
And they were incredibly strict about what made it through, right? They aggressively filtered those 40 million videos down to just 0.8 million highly accurate sequences.
Right, which is a huge cut.
Yeah.
But importantly, about a third of those sequences that survived contained dynamic, moving objects that the system actually managed to handle correctly.
Which is huge for training a robust model. So by combining this newly filtered data with existing data sets, they built a supervised data set of 4 million diverse scenes.
Which, again, is 15 times more supervised data than the original model had. But as you look at the paper, they didn't stop at supervised data.
Right. They also utilized 18 million completely unlabeled videos. And this is the part I really need you to clarify.
Sure.
How do you teach a geometric 3D reconstruction model without providing it with ground truth geometry? Like, what is the actual mechanism for learning depth from a video if you don't tell the model how deep the scene actually is?
So they use a self-supervised protocol that was heavily inspired by a system called Dino. It works on a teacher-student architecture.
Okay, teacher-student, walk me through that.
Imagine you have two identical models, a teacher and a student. You initialize both with a supervised VGGT Ω checkpoint. Then you feed both models the exact same input video sequence.
But they don't see the exact same thing, do they?
Right. For the student model, you apply heavy augmentations. You crop the video, change the colors, and radically shuffle the order of the frames.
So the student's basically looking at a distorted, scrambled version of what the teacher sees.
Exactly. And the student's job is to predict the geometry and mathematically match the feature distributions that the teacher model is outputting on the clean video.
And how does the teacher improve if it's just outputting features?
That's the trick. The teacher doesn't get trained directly through backpropagation. Instead, its weights are slowly, iteratively updated using an exponential moving average of the student's weights.
So by forcing the student to match the teacher's understanding of the scene, despite seeing a scrambled and cropped version, the model is essentially bootstrapping its own geometric understanding.
Precisely. It learns that a car is a 3D object regardless of which frame it appears in or how it's cropped or what color it is.
That is brilliant. It enforces geometric consistency across 18 million raw videos. And if you look at the graphs in the paper, you see the direct result of this data pipeline. You get these incredibly consistent power law-like improvements.
Yeah, as they scale from 0.2 billion up to 10 billion parameters and from 2,000 to 2 million sequences, the performance just scales beautifully.
I want to highlight the benchmarks here, too, because it is important to contrast how this feed-forward model operates compared to the older optimization method.
Yeah, absolutely.
MegaSAM is a heavily used post-optimization method. But optimization methods essentially have to painstakingly solve the geometry for every single new video, frame by frame.
Right. It is like doing a complex math puzzle from scratch every single time you hit play.
Exactly. Whereas a feed-forward model like VGGT Ω just looks at the video and instantly guesses the right answer in one shot.
And despite guessing in one shot, it is vastly more accurate. On the Sintel benchmark, researchers use a metric called AUC at 3 degrees.
Which measures the area under the curve for errors under 3 degrees, right?
Yes. Essentially, it scores how consistently accurate the model's camera angle estimation is within a very tight 3-degree margin of error.
Okay, and the scores.
MegaSAM achieved a score of 22.5. VGGT Ω hit 40.0.
Wow.
Yeah, it nearly doubles the accuracy. And because it is a single feed-forward pass, it operates 50 times faster.
Okay, so we've covered the memory fixes, the data scaling, and the benchmarks. But here is where we get into the truly striking results of the paper.
The emergent properties.
Yes, because when you take a 10 billion parameter model and you force it to predict 3D geometry across millions of videos, it doesn't just learn geometry. It starts understanding the physics of the world in ways it was never explicitly programmed to.
Right. These are the emergent properties of scale. The researchers discovered what they call motion awareness.
And it is crucial to note that the model was never given optical flow data for this, right?
Never. It was never given ground truth segmentation masks for moving objects either. But the researchers took the intermediate image tokens from the network, normalized them, and just applied a simple PCA clustering.
For those listening who might not use PCA, principal component analysis is basically a statistical way to group similar data points together without knowing what those data points actually represent in advance. It just finds mathematical similarities.
Right. And with 0 labels, the PCA clustering revealed that the model naturally separates moving objects from the static background.
There is a specific visual example in the paper that illustrates this perfectly. It is a video of a breakdancer performing in front of a static crowd on a street.
That's my favorite example in the paper.
It's so clear. If you look at the PCA clusters in the early layers of the network, like around layer 4, the model cleanly isolates just the moving dancer. The static crowd is entirely ignored. It is essentially doing perfect zero-shot motion segmentation.
But what's really fascinating here is how the representation evolves through the depth of the neural network. While layer 4 isolates the sheer physical motion of the dancer, by the time you reach the deepest layer, say layer 23, the clustering shifts completely.
Right. It stops highlighting just a moving dancer and starts highlighting all the people in the scene, both the moving dancer and the static crowd.
Exactly. The representation shifts from purely physical motion to semantic categories. The geometry model basically realizes, oh, these objects share the same structural category. They are all humans.
And that brings us right back to those register tokens, those 16 delegates we talked about in the memory section.
Right. Because those delegates act as an information bottleneck, they are forced to encode these high-level semantic summaries of the scene.
So the researchers wanted to see just how semantic these geometric registers really were, so they attempted to align them with a vision language model.
Yeah. They took a frozen VLM, which is designed to generate text descriptions of a scene. Then they took the geometric register tokens from VGGT Ω and used a symmetric info and loss to align the two embedding spaces.
Which, think of an info and C loss as a mathematical sorting hat. It rewards the model when the geometric shape of an object, say a person, matches the text description of a person, pulling those data points closer together.
Exactly.
And it penalizes the model when they don't match, pushing them apart. But importantly, the language token they introduced only ever looked at the geometry registers. It never saw the raw image patches.
And it works seamlessly. Without degrading the 3D reconstruction performance at all, the purely geometric model aligned completely with the human language space.
Which is just a stunning confirmation of the Platonic representation hypothesis.
Yes.
Which argues that if you train capable models on completely different modalities, like one model trained purely on text and another trained purely on the 3D geometry of video pixels, they will naturally converge on the exact same underlying mathematical representation of reality.
Exactly. The geometry model learns what a person is, not because we give it a dictionary definition, but because a person occupies and moves through 3D space in a highly specific, structurally consistent way. The geometry inherently dictates the semantics.
It's beautiful in theory. But I want to push back on this idea of a perfect Platonic understanding, though.
Okay, let's hear it.
If it truly understands the concept of a human on a semantic level, why does it suffer from the humans and walls problem? The paper specifically notes that when the model looks at near-static street view videos, it occasionally just absorbs pedestrians into the background geometry. Like it predicts that a walking human is literally part of the brick wall behind them. That doesn't sound like Platonic intelligence. That sounds like it is just blindly memorizing bad data.
Well, you are entirely correct. It is blindly memorizing bad data. This is a perfect example of a dataset artifact becoming embedded in the model.
So where does the artifact come from?
It comes from the widely used megadepth dataset, which relies on coal map annotations generated from internet photo tourism images. Because people naturally move between different photos taken of the same tourist landmark, the patch-match stereo algorithm gets deeply confused at the boundaries of humans. It erroneously assigns the pixels of the person to the static architecture behind them.
So the training data is explicitly teaching the model that humans are load-bearing brick structures.
Exactly. Garbage in, garbage out.
But if we know the model learned this bad habit, how do we fix it? Or even find where that habit lives inside a 10 billion parameter brain?
They found it through an experiment they ran called model souping.
Model souping?
Yeah. This involved directly averaging the weights of two different models without doing any extra training whatsoever. They took the weights of the old public VGGT model and averaged them with the new VGGT Ω model.
Which sounds mathematically insane. It's like taking two different chef's recipes for the exact same soup, literally pouring them into the same pot and somehow expecting it to taste better instead of turning into an inedible mess.
I know, it defies all intuition, but it works. It produces visually reasonable 3D reconstructions. And by selectively fusing only specific subsets of the weights, they could mathematically probe exactly where different types of information are stored.
And what do they find?
They discovered that depth and field of view information is primarily stored in the feed-forward networks, the FFNs, of the frame-wise attention blocks. It is not stored in the query, key, or value projections, as you might expect.
Wow, and this solves the humans and walls problem.
It does. When the researchers took just the FFN weights from the original VGGT's frame-wise attention blocks and fused them into the Ω model, those specific humans and walls errors completely vanished.
That's amazing.
Yeah, it proved mechanically that the model had stored those bad geometric habits entirely within those specific FFN layers.
It is an incredible piece of debugging. They pinpointed the exact lobe of the network where a specific dataset bias was stored, and they corrected it without having to retrain a 10 billion parameter model from scratch.
Which would have cost a fortune in compute.
Absolutely. So to synthesize this entire journey for those of you listening, the researchers started with a hard technical bottleneck, VRAM. By introducing register intention and ripping out memory-heavy convolutions, they bypassed the quadratic cost of global attention entirely.
Right.
And that optimization freed up the memory required to unlock LLM-style scaling laws, allowing them to train massive architectures on an unprecedented 22 million videos. And that scale didn't just achieve state-of-the-art 3D reconstruction, it resulted in emergent motion awareness and deep semantic understanding. It proves that the future of perception isn't about building isolated tools for depth, separate tools for segmentation, and separate tools for language.
Yeah.
The future lies in unified, multimodal models that understand the world holistically.
And that leaves us with one final, deeply provocative thought to consider.
Let's hear it.
We just saw that a neural network trained purely to predict the physical 3D geometry of pixels naturally develops an internal representation of the world that aligns perfectly with human language.
Right.
It raises a really fundamental question. Is language actually just a byproduct of physics and geometry? As we continue to scale these models, we might not just be building better 3D reconstructors. We might be reverse engineering the mathematical structure of how intelligence perceives reality itself.